like a light switch, right? So there's two ways that you can turn on or tell somebody to turn on and off a light switch. You can tell them turn it on and then turn it off and then turn it on and then turn it off. Or you can tell them turn it on and off every second, and they just go click, 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 click. Or every thousandth of a second or 1 millisecond, they go click, 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 right. So those are kind of different ways of inputting that information. So the way it's set up, this top one on this, if you look at it with GT facing you, that one is the counter input. So in LabVIEW terms, when you tell it to do it at a particular frequency, that's called a counter line. If you say you just want to turn it on and off, that's the digital I/O line. All right. So this top one up here should be connected to the top port on the digital I/O DAC, and then the direction, which is the second one, can be connected to any of the other three. While we're talking about this device, this is a current limiter. That's kind of a big motor. You can run it at 6 amps and it'll work fine. It's pretty torquey. That means it can pull lots of weight. That's a good thing. So I would leave that at the rightmost as you're facing the device. That way you put a lot of current to the motor. This thing's also built with a dead man switch. That's that red button right there. So the way a dead man switch works is you push it, you hold on to it. If you get off of it, it just cuts off the power immediately. All right. So you should always physically push it, and the person that's pushing that button is the person that should be looking at the linear actuator. So if it gets close, you just get your finger off of it so you don't damage the hardware. All right. The first thing you do when you try to connect the hardware to your DAC is to go to Measurement and Automation Explorer. And this group, Rem has already done this, but I'm going to do it again. So we'll go to Measurement and Automation Explorer. It's already connected. This is station 4, which is fine. So the way you connected that, you click on it, you unreserve and re-reserve it, just to make sure you are the one that's connected to that DAC. And then we're going to test the load cell first. On the load cell, there's the gain part here. So first of all, the high pass frequency should be DC just like before. So you don't want to look at you don't want to worry about the low frequency stuff. So you just want the DC component. The low pass filter, the process that you're doing is kind of fast. So the Earthworm lab was kind of slow, right? It contracted very slowly. This one is going to happen kind of faster. So you should be at 150 or 2,000 hertz on the low pass filter. And the gain, so it's 50 pounds per 3 millivolts, so that's the conversion factor. So if you had 1,000 time gain, it means that you could go up to 30 volts, right? And that's too much. So you don't want to be at 1,000 times gain. You want to be at 100 gain at the max on that. So while I've got that set at 100, I'm going to go back to the first module on the Ethernet chassis, go to test panels just to make sure it's working. You should always do that when you're connecting to hardware through Measurement and Automation Explorer. So on this station, it's connected to AI1, station 4, mod 1, AI0 is the first actual physical channel on there. And then the mode should be continuous. And then you hit start. I didn't hit continuous. I said continuous, but I didn't hit continuous. Sharon, do you mind pushing the DAC a little, just so we can see it? So the DAC is that silver thing. So just push the, yeah. Okay. So you can see that it works fine, right? So we know that the load cell is working. I'm going to hit stop. Close that DAC, open the digital I/O DAC through the test panels. On the top, you'll see digital I/O and counter I/O. We're going to try to move it, so we're going to go to the counter I/O. CTR0, that's the top line, so that's where it's connected. It says it's going to go at 1,000 hertz. 1,000 hertz is kind of slow with this DAC, so I'm going to hit start. Now, you notice that it's not actually moving. It's not moving because no one pushed the dead man switch, so I push the switch, and then it moves. All right. So it was moving that way toward the grip. I'm going to stop it, go to the digital I/O. The second line is connected to the second DAC line, right? So that's this. So this 0 is the first line, 1 is the second line. I switched it from an input to an output, and then it was set on low, and I'm going to switch it to high. And I'm going to hit start and then stop. So within iHardware, if you change it from a low to a high state, it stays on that state until you tell it to go to another state. Alright, so it retains its last value. It's not like it fails off or fails on, it just retains whatever it was before. So right now I switch the state, and then I go back to the counter line and I hit start and I push the button. And it goes the other way. So we know it all works, right? So that's a good thing. If you guys are not interested in the LabVIEW portion of this, did you download the executables from?
Is it in our SharePoint folder?
Yes. So in your LabVIEW EI portion, this is Chrome. So I'm going to download that. It's an executable, so it wants you to not save it. Just say keep. That way it actually saves it. And then when you show it in the folder, you have to extract all. Okay. So we'll do the linear actuator first. So it's called sit easy direction, and I hit run. Alright, so we have to change some of the settings. Right now when I wrote this, I did this on station 3. So this is station 4. The motor was 3110 station 4, mod 2 CTR 0. The motor direction, again, everything needs to be station 4. Mod 2, port 0, line 1. So there's only one port on that digital I/O DAC. Port 0, line 1, which is the second line. So that's right. AI channel is station 4, mod 1, AI 0. Now the test movement rate is the movement rate that you want to actually test your sample at. So that really depends on the standard. I think it's 20 inches a minute or 500 millimeters a minute for the D412. It's written in there somewhere. In any case, you want to set that before you hit begin testing. Alright, so what that begin test does is it actually begins your actual run. So I click begin. One of the things I forgot to do is change the amplifier gain. So I'm going to switch that to 100. Now it's calibrated. Alright. I'm going to tear it to 0 it. And then maybe you could give it a nice tug and so we can see how strong you are. So that was 11 pounds. That's pretty good, right? That's so this is units in pounds because it's pre-calibrated now. All right. Now, if we want, we've got your samples that I'm going to give you. The samples are that dumbbell or dog bone shape. They're kind of small. We got to position the linear actuator to where the clamps can actually work. Do you mind pushing that red button?
Sure.
All right. So that's where the nudge comes into place. Now, this direction change, some of these stations, when you nudge up, it goes left. Sometimes when you nudge up, it goes right. It depends on the way the wiring goes. So go ahead and keep the button pushed if you don't mind. And I'm going to nudge up. And it's going that way, so that's good. Now I'm going to nudge down. So again, I'm going to try to bring them kind of closer together so that... Okay, so in any case, you've got it in position, you put your samples in. When you got that dumbbell specimen, there's two rectangular regions on the periphery, and there's that central rectangular region in the middle. Now that's your test region, that central region, right? But you have to clamp onto the peripheral region. on this setup, you really want to cinch up on it as much as you can, as close into the triangular part. That way when you stretch it, it'll break before it ends. If you clamp right close to the ends, you'll stretch it all the way and it won't break. Alright, so just make sure you do it on the peripheral reticular region, but just as close in as you can. The grips are just hand-tight grips. If they're slipping out for you, and you can try with just regular gloves that you just cut with a scalpel blade or something, or a pair of scissors, but if they're slipping for any reason, just put a piece of tape around it, and that way it gives you a better grip surface. Of course, you don't want the tape on the rectangular or the triangular region that's in the middle, just on the periphery. And that works fine. Again, you just click test and hold on to test. Do you mind pushing it one more time? And that's always just going to go at whatever rate this says, 100 millimeters a minute. So that's the load cell and the linear actuator, and it stores this data. So whenever it says stop, just put in a text file or a CSV file, and it stores that for you. So let's look at the camera right now. This camera is connected not very well. On this station, it's called Cam 1. You can always go to here and hit snap just to make sure that the camera is working. And it is. It is working fine. So we know it's fine. So now we can go back to SharePoint. I don't know, but I don't think I can allow access. That's the admin privilege problems with our computers. In any case, I think I actually saved it already. Let's see. I don't know who this is. Extract all, extract, open folder. So this one's called grab ROI and save. So the first time you run it, it's trying to store it on a location where these computers don't have access, right? So it's going to error out. You just have to wait just a second for it. And then you'll have to hit stop. Okay. The first real step is to try to find a location where you can actually save an AVI. So I'll click is it okay if I save something to the desktop?
Yeah, that's fine.
Alright. So I'm just going to call it test.avi and hit OK. Now we were Cam 1, right? And then we can start. So we know it works fine. The only reason I wrote this is so you don't have to record the entire image, right? So normally when you do this, you're going to have a pretty thin little area where you're stretching your sample. You don't need all that information on all the sides of it, so you can just set your ROI like that, and then you can start recording, and now it's recording. And then you can hit stop. But otherwise, if you don't want to use this, definitely you don't have to use this. You can always just use your phone or something. It's just, you'll see that the size of it kind of gets a little out of hand if you're running it at 120 hertz on your iPhone. It'll get kind of big. Okay, so anybody want to try the LabVIEW part? Yeah? So I'll show you guys how that generally works. I think you've got it open here. So you still want to set this all right. So it's Station 4 Mod 1 AI 0. That's what it's connected to. It was backwards, right? So it looks like it's on the third, but on this DAC it's just tilted the opposite way. So it's AI 0. This one should be Mod 2. I think it was called CTR 0. This one is still Mod 2. Port 0, line 1. Again, you'll find that out in Measurement and Automation Explorer on whatever it is. Now this is the force sample rate, and that's the test movement rate. And the test movement rate here is steps per second, not units of millimeters or something. So the conversion there is that we've got a stepper motor, which is 1.8 degrees per step. And then we've got a power supply and a micro-stepping driver that every time you tell it to make one step, it actually makes 1/10 of a step. So if you tell it to move one step, it actually moves 0.18 degrees. So if you tell it to move 2,000 steps, it goes one revolution. All right, so 2,000 steps is in a revolution. If you tell it to go 2,000 hertz, it'll go one revolution a second, right? And then if you want to go, so the linear conversion there is it's 5 turns per inch. So there's a screw in there that's 5 turns per inch, and then you just make that conversion to get to 20 inches a minute, or I think it's 500 millimeters a minute. Either way, you put that in there. The other part about this VI is that I kind of try to split it up for teamwork purposes. So there's this top loop that's all the image analysis stuff. All right. So what it starts with is an image input. That's this thing right here. And what you needed to go is from an image input to a distance or a strain. All right. The second loop is all the load cell stuff. What you have is raw force data, right? And from the raw force data, you need to go, well, by raw force I mean in voltage, right? You need to go to force and or stress, right? So that's the conversion that you need to do there. This third loop, you don't mess with it at all. That's the linear actuation stuff. You should not mess with that. The fourth loop is a way for you to connect the first and second loops together, because in the end you want an XY graph, and that's actually done for you here. That's the XY graph that you need. And that is stress versus strain. All right. So what, in LabVIEW terms, what's nice about LabVIEW, I guess, is that it's a real-time software, so that if you've got a loop running at a particular rate and another loop that's running at a completely different rate, it kind of connects it all together in one loop at a third rate that you're actually interested in, and it all works without you having to worry with it. So in any case, this fourth loop is a place where you kind of combine the distance or strain and the force or stress together. All right, any questions, concerns, issues?
Do we put the steps to modify the LabVIEW module into our flowchart?
Yes. If you're going to do the LabVIEW part, you should include that in your flowchart. If you're going to do something else, whatever you're going to do in the module should be in your flowchart. So there was a question in one section that said, can we use the executable to do our samples and then do this? And that to me is kind of goofy, because you're basically doing twice the work, right? This makes your analysis easier, not harder, if it works right. So if this works, you should definitely use this. But you know, again, it's up to you guys what you do.
Can you also mention what teams can do if they don't want to do LabVIEW portion?
You guys don't have to do the LabVIEW portion. There's the 3 deliverables that you have to do if you want to turn in your report. So that's the standard that I provide for you. That's the stress and strain. And then you pick a second standard, and then I'm going to give you some data as soon as I get a chance to generate some data from the instrument next door. And then I'm going to use D412 for that, because everybody's doing it, and I'll probably just use the autoclaved or one of the groups, and then you use that data to compare it to yours to look at precision and accuracy kind of questions.
So for the standard that we chose, can it use the D412 testing methods, or does it have to be completely different?
Huh?
So like we chose a different standard.
So there's other standards that, for example, the one that I can recall that people have done in the past is the aging one. So there's one that kind of looks at the impact of aging on vulcanized rubbers. Is that kind of what you guys are thinking about? So there, what that the standard that they're talking about, correct me if I'm wrong, is that it's an aging protocol, and then it says use D412 after you age it. And there's nothing wrong with doing that. So you can still use the same standard, but you're using a different standard. It's just that you're using that standard to age your sample. And the tricky thing about that particular standard is just remember the objective of the module is to see the effect of sterilization, right? So really for that, and I don't know, we can talk about this offline, but really for that particular standard, the hypothesis really is that there's some effect of steam sterilization on aging, right? So what you're really saying, if you think about it, isn't that the gloves age, because we know they do, right? Vulcanized rubbers get more brittle over time. It's that, and we know that, we think, at least theoretically, that steam sterilization impacts it kind of the same way. The real question you're asking when you do that standard is there some interaction between steam sterilization and aging that's worse than anything else, right? So from a product development point of view, you want to have a longevity or a shelf life for that thing. What you're interested from a scientific point of view is to see if there's some interaction between aging and steam sterilization. And there's no way to analyze that except with a two-way type of analysis, if you know what I mean. Okay. So a one-way analysis is not sufficient to answer that question, because you can test an aged sample and a non-aged sample, a steam sterilized sample and a non-steam sterilized sample, add the two together, and that still doesn't explain what happens with aging and sterilization, because you're kind of ignoring the interaction parameters. All right. Other questions? Sorry, too much info.